All right, I think we are live. So welcome everyone to Radiation Belts and Space Physics. Our today's online seminar is dedicated to Earth ring current in coupled geospace. And we have two fantastic speakers for you this afternoon. Matina Gkioulidou from APL will be talking about new exploration, experimental approaches to understanding couple geospace at the systems level. And Anthony Sciola, also from APL, is going to dive into the recent results on global simulation and the analysis of simulation data of the buildup of the ring current.
Hey, so, Sasha?
Yes.
I apologize. I accidentally clicked the leave button. I don't know if anybody had any questions, but I'm sorry.
Thank you. For the sake of time, Scott, I think we should move on. Much appreciated. We know how to reach you. So for the sake of time, I think what we're going to do as usual is that we will do the talks first, and we will hold off on the questions for the end of the seminar. So without any further ado, Matina, the floor is yours.
Okay, thank you. Let me share my screen. You will see a presentation, and let me put it. Okay, can you tell me what you see?
It's getting, so far it's blank, Matina. Oh, we're seeing presenter notes. I can see that. That's the problem.
So, any quick hints how to change the...
Do you have two screens, Matina?
I do.
I think
right.
you selected the wrong screen to present.
Okay.
You need to switch screens.
All right, let's try to do this again.
Meanwhile, if anyone has questions for Scott, this is your time to.
Figures out how to protect.
Let's try this again. Excellent. Looks great, Matina. Go ahead.
Okay, great. Awesome. Okay. Good afternoon, everybody. Yes, my name is Matina Gkioulidou. I'm from APL. And today I will be talking about how we can observe the global geospace in mesoscale resolution and why I think this is very important to do in the near future. And I have to say I'm emotionally charged because I'm giving an RBSP talk after a while, and I think I might have given one of the very first ones after the RBSP launch when we were starting getting data, and I was a postdoc back then. So time flies, but here we are. Okay, so why do I want to talk about mesoscale processes? I use that analogy from Eric Donovan, actually, who very nicely said that the mesoscale processes are the bridge connecting the local and global nature of geospace. And it's I chose that picture to put there because I think we are at a point where we know they're important, but it's a very shaky bridge, and we are kind of afraid to cross it. But I don't think we have any other option. We certainly do need to cross that bridge in the next decade. So just to put things into perspective, understanding geomagnetic disturbances to the level of predictability, still after decades of space research, remains elusive. And I think this is because we still do not understand the mesoscale processes, and by mesoscale, we need to put some numbers down. We're talking about maybe 1,000 kilometers to pure in the magnetotail, depending on the processes you are looking at, and tens to hundreds of kilometers in the ionosphere. So we don't understand those processes, and most importantly, we don't have a good feeling for their global implications. So I will talk about two different aspects of this. The first one is the effect of mesoscale transport on ring current buildup. So what we know so far, in situ observations throughout the decades have given us a good handle of how space is more dynamic and more fine scale than we are used to think about it when we think about global disturbances. In the plasma sheet, for many years, starting from geotail and then Themis did revolutionize the field a lot. There have been observations of processes like bursty bulk flows and depolarization fronts. And those were accompanied by enhanced energization of particles in the plasma sheet. On the left, you see a study of that sort from the Themis era, Runa et al. 2011, where it's a statistical analysis of those kind of features that have been widely observed in the plasma sheet. On the other hand, on the inner magnetosphere, we have back even from the, without the geosynchronous satellites, there have been a lot of observations of energetic ion injections. Then RBSP came about, Van Allen probes, and more studies have happened to statistically analyze these kind of injections. On the right, you see a study by Matina et al. In 2018. And you see that there are common features between what we see in the plasma sheet and what we see in energetic ion injections in the inner magnetosphere, but the connection is still not very well understood. And of course, we have the modeling component where these guys over the last decade, they had made huge advances in their models. They have pushed the limits of resolution. And all kinds of different models, but especially global magnetohydrodynamic simulations are showing that you have these depolarization fronts happening from the plasma sheet to the inner magnetosphere. They carry particles with them, ions, and these are the features that actually build up their ring current, the pressure in the inner magnetosphere. I will not say too much about it. I'm sure Anthony, who is following me, he will tell you a lot about that stuff. I just wanted to mention this because I think the models have pushed the limits, but we, as every model have their own caveats, so we kind of have to put them to the test with observations that hopefully will be coming in the next decade. So what we don't know about mesoscale injections, it's a challenge to assess observationally the global consequence of these observations. Yes, the models tell us they're important, but how do we check that observationally? On the right, you see a figure from actually my first paper with RBSP data back in 2014. It was during the first big geomagnetic storm we had, the March 17, 2013. And, back then I saw these injections in the inner magnetosphere. That's how they show up from a single spacecraft. And you see, you have low pressure before, then injections, then high pressure. So I started thinking, okay, maybe then that's it. You have lots of injections coming in, and that's what builds the ring current. And of course, when I went a little bit deeper to do the analysis, I discovered that it's very hard to make assumptions of the size of injections, of how much energy they carry, and how much they contribute to the inner magnetospheric pressure. Nonetheless, with all these caveats, we made an estimate of 30% of the contribution of the plasma pressure in the buildup of the Earth's ring current, at least for that geomagnetic storm, was coming by these more dynamic localized injections. But on the left, I want to show you how trying to do that with this situ spacecraft is very hard, because let's see that MHD models are correct and you have all these features coming in. If you have a spacecraft sitting there in an orbit, yes, it's moving around, but every time it will just see one of these features, or maybe a second one if it's over here, but you miss a whole region that you cannot observe at the same time. So this is another analogy I want to use by David Sybeck. In a sense, it's you can think about it as like trying to predict hurricane evolution, having single weather stations. Now we are very used to these those images, but back in the day it wasn't very easy to predict the evolution of these weather disturbances. And of course, yes, in the inner, studying these features in the magnetosphere has been a challenge over the years, because on the one hand, you have the spatially confined nature of the in situ observations, which lack global context. And before I mentioned one spacecraft, I know there have been a lot of efforts and studies where people are trying to look at data from different satellites. This is a good example here, studied by Turner et al. 2017, where he made an attempt to estimate the injection extent and evolution using 16 spacecraft, which was a rather serendipitous conjunction. These are not coordinated observations. And the conclusion of that paper is like, yes, we think this is happening, but it really challenges our understanding of injections. So we cannot really tell how injections are evolving. So you have that with in situ measurements, and on the other hand, the other technique that has been used to image the ion dynamics in the magnetosphere is through ENA emissions, energetic neutral atom emissions. So you have the ENA imaging, but on that front, for years we have had limited temporal and spatial resolution. And I know that recent studies by Kiesel et al. From Twins data are trying to push these limits, but you have to think that all these instruments are maybe 20 years old. So we can definitely do better in the future. Now, moving on to the mesoscale magnetosphere-ionosphere coupling. And I'm moving a little bit out of the inner magnetosphere. However, what I'm going to say here, it's very important to what I have already mentioned, because, you know, magnetosphere is not a system by itself. It is coupled with the ionosphere and even with lower down the atmosphere, but I'm not going to get there for this presentation. So you have auroral phenomena ranging from mesoscale auroral streamers to the global brightening of an auroral substorm, and their manifestation of both the energy deposition within the strongly coupled MI system and the ionospheric conditioning itself. And here I'm listing all kinds of phenomena that people have given very interesting names to their, and I want to mention two very nice review papers. I recommend you go and read them to get a sense of the literature and the studies that have been done studying this phenomenon. However, we still don't know how all these mesoscale features in the ionosphere that we observe in the ionosphere, how they relate to mesoscale features in magnetosphere. We know there must be a connection, but how they're connected exactly, it's not well known. For example, how do auroral streamers evolve spatially and temporally with respect to plasmacyte mesoscale structures? There have been a lot of implications, a lot of papers talking about the connection, but I don't think we have a definitive answer to that. And again, it is very challenging to assess observationally the global consequences of mesoscale processes, even in the MI coupling, the MI coupled system. People have talked about the substance current wedge that others believe it's a conglomeration of streamers and wedgelets, or others think that is a more global and coherent structure that is happening. And there have been papers actually emphasizing that it's the parsed burst component of the substorm evolution is a key factor in the excitation of geomagnetically induced currents, which are very important for the space weather. And moving on with other mesoscale features in ionosphere that are very important, there have been two very recent papers in 2021 where they emphasize using ground-based auroral sky imagers about how the mesoscale precipitation seems to be very important when we talk about energy deposition during geomagnetic storms. However, ground-based imaging cannot address how much mesoscale precipitation can impact global total precipitation, or how mesoscale precipitation varies with the hemisphere and seasons. It's more localized, the observations, that is. So, okay, I think I'm good with time. In my last slide, and then I will give the floor to Anthony, I want to talk about, I gave you an introduction about all these challenges, and I want to talk about what we can do going into the new decade. I want to mention the mission concept we put in the as a white paper for the decadal survey to look at. The mission is called Paragon. We actually, and here you can see all the people involved with this idea. It started as a proposal for heliophysics mission concept studies like a year ago. So we were one of the selectable missions, but unfortunately we didn't make the final cut. But then we decided to propose it as a white paper to the decadal survey, with the hopes that maybe the decadal survey itself can do this study. And what Paragon is trying to change a little bit the paradigm of how we are doing observations. It's an idea that in order to answer these questions, you need both imaging component of observations and in situ measurements at the same time and coordinated. And that can happen with a big mission, or maybe it can happen with coordinated missions. I don't know, up to the decadal to decide that. But for example, here you can see, all this activity happening in the tail, depolarizations, injections, ionospheric activity at the same time, auroral features. And then imagine that you have in a circular orbit, we baselined it at 9RE. You have 3 spacecraft that are following each other in that orbit, and they have global imagers, ENA imagers for the recurrent plasma sheet, FUV imagers for the aurora, and visible imagers for the aurora, and EUV imagers for the plasmasphere. And you have these remote sensing platforms are 3-axis stabilized spacecraft in, as I said, common polar circular orbit. And you get simultaneous dual hemisphere imaging of the auroral ovals having these measurements. And the important thing that I want to mention here is, again, it's not just having old instruments up there. Imaging instruments have developed over the years. They have advanced in resolution, both spatial and sensitivity. So I think we will be able in the new decade, if we have a mission like that, to have a much more high resolution images of the magnetosphere and ionosphere system. And then at the same time, it's important to have in situ component. And we baseline something cheaper in this case for spinning small satellites in near equatorial elliptical orbits. You can see them here with these type of orbits. That now how far they go, it could be 10-ary, it could be 6-ary. Again, it's all about the money. And this type of spacecraft would have plasma, energetic particle sensors, and magnetic field measurements. So I think you get the best of both worlds. You have the in situ measurements with very detailed observations of the plasma, and then you have high resolution global images of the aurora and the plasma sitting in our magnetosphere. And I believe these are the coordinating measurements we need to answer all these questions I talked about in the presentation. And I will leave it at that, just in time for Anthony to pick it up, I think.
Thank you, Matina. As I mentioned earlier, we're holding off all the questions and discussion for the end of the seminar. And if you stop, we'll stop sharing. We can give the floor to Anthony. Anthony, please go ahead.
All right, can you hear me and see everything fine?
Yes.
Okay, great. All right, thank you. All right, so my name is Anthony Sciola. I'm a postdoc here at APL. I'll be talking about partially the buildup of the storm time ring current via essentially BBFs, but also look at some characteristics and relationships between the BBFs themselves and the associated depolarizations and injections that go along with them. Assuming I can click forward. Okay. So just a bit of background, Matina already gave a very nice introduction to these, so I won't spend too much time on it, but we know that BBFs are responsible for transporting both depolarizing flux and fresh plasma in the form of injections. But the picture is a little more complicated than that. For example, looking at this schematic from Gabriel's 2019, they're showing a schematic for how continuous depolarizing flux bundles can lead to a flux pileup, and this not only alters the drift orbits of plasma at previously lower L shells, so that when you see an injection signature, it could actually be these this lower population reaching up to your spacecraft, but also this pileup affects the evolution of subsequent flows behind it, and so the exact relationship between the PBS themselves and then depolarizations and injections that you might see is not completely clear. There's also some open questions about the exact sort of one-to-one correlation between these three things too. For example, in a paper by Runeval last year, they showed that they observed 21 depolarization events at Geo, but only 10 of those had an accompanied injection with them. So it raises the question, were these depolarizations and injections still driven by BBF? So we didn't see these two quantities simultaneously. And then I don't know why. There we go. Okay. And then, as Matina has already hinted on, there's been a lot of work so far trying to understand exactly how much the injections associated with these BBFs are contributing to the ring current buildup. And so, of course, there was Matina's estimate from the March 2013 storm that predicted about 30% of the total pressure was coming from these injections. There was a study by Young et al. Using the standalone RCME model that found that about 60% of the total energy density within 6RE or geosynchronous orbit was coming from bubbles versus non-bubbles, i.e. sort of convection in this sense, and already trapped particles. And then Kramer et al. With OpenGGCM, MHD model, and RCM also had a nice study showing that these bubbles are responsible for transporting a significant fraction of the total inward plasma, that really poorly, basically responsible for transporting a whole lot of plasma to the inner regions of the magnetosphere. And then also there was a study by Strathe et al. Last year that looked at the characteristics of these bubbles in the tail based on the entropy depletion inside of them. and found that these low entropy bubbles account for roughly half the total energy transport, while making up only 15% of the total plasma population. So that's sort of a bit of observational and simulation background on how important these could be to build up of the ring current. And so what we're going to do is we're going to do a case study on the March 17th, 2013 storm using the MAGE model, which has been featured a couple times here, including the Gamera model, which you're seeing the equatorial view here on the left, and then meridional view on the right. That includes the Ionosphere potential solver in these two hemispheres here, and then also the RCM in a Magnetosphere model all coupled together. So our goal here, of course, is to study the relationship between the depolarizations and injections associated with BBFs that we see, and also investigate the characteristics of sub-geo penetrating injections and their contribution to the ring current. So we're not really worried about how many make it into geo. We're mostly just looking at the ones that do make it there. How much do they contribute themselves? And of course, the reason why we're doing this is it's better to understand these processes for their own sake and understand how the system is coupled together, but also from a geospace modeling perspective, we'd like to be able to model this well, because it's important if we want to be able to still consistently reproduce the features like the ring current radiolocation, its azimuthal extent, and the intensity across all energy ranges that we're hoping to model. And this in turn is important if we want to be able to self-consistently model things like precipitation, the resulting ionospheric conductance that you get from that of course all couples back, and the energy dependent loss processes. It's all dependent on getting the buildup right in order to lose the right population in the first place. So this is a sort of quick overview of the simulation. On the top panel, I'm showing common DST plot, and then I'm showing three variables in the equatorial plane: the total pressure, the radial velocity, and delta BZ for 4 different time steps. Looking at the DST plot, you can see in blue the observed SMH, and then in orange the Biosavart calculated DST from the model evaluated at the center of the Earth. So it's not of course going to produce exactly what the real DST shows, but they're in pretty good agreement here. Then I'm also showing the DPS DST within 6 area evaluated and the entire closed field line region within 6 area. I'm showing it here not to compare with the other 2 DST plots, but just so I can put everything on the same slide. I'm using it as a proxy for understanding when the ring current was really built up during this storm. And so you can see that the DPS DST is relatively flat up until about 8:30, and then it drops quite regularly until about 10:30, depending on where you want to draw that minimum there, and then it flattens out again. Then we can look at these 4 different time steps, before this DST drop starts. You don't really have much of a ring current, and then during this drop is when you're building up your ring current over time. You can see multiple BBFs with these inward radial flows and associated depolarizations. And so this is obviously carrying a lot of magnetic flux with it. And then we'll also look at how much plasma pressure it's contributing as well in a little bit. Before we get into that, I'm just going to show a quick comparison with ion intensities from RB-SPICE. On the left, I'm showing a comparison from RB-SPICE up top and RCM on the bottom of the whole energy range between 10 and 200 keV. And then on the right here, I'm showing that same quantity, but for 10 select energies as line plots here. So we can see that we're not starting off with the most accurate initial ring current, but when you get through the ring current buildup phase, and then we finally come out on the other side here, where we have RBSP data again, we can see that we're agreeing quite well, and it shows up very well on this line plot here. Of where the ring current location is, the intensity of it, and the intensity across many energy ranges. Not completely, but pretty good agreement there. And so this gives us some sort of confidence that we can gain some insight from this simulation. And then it doesn't match up as well after around hour 12 or so, but we're mostly concerned with the buildup between around 8 to 10 hours there. Okay. So the first thing we're going to look at is try and look at the injections and depolarizations that are associated with the BBFs that we get in the model. And we're going to do that by taking this semicircle at 6RE along the night side, and look at that as a function of MLT here on the y-axis and time in x. And this top panel is the enthalpy flux, which is the radial component of the enthalpy flux, which is essentially pressure times B perpendicular to the magnetic field, the radial component of that. The second panel is delta BZ, and then on the bottom we have the flux tube entropy all through this night side arc here. So we can see many BBF structures here, and they're indicated by the coincidence of enhancements in the inward enthalpy flux, which I'll just make sure to mention. Inward here I'm highlighting as red, since it's contributing to the ring current is the idea for that. We see these enhancements in inward enthalpy flux with simultaneous depolarization events, and as expected, entropy depleted bubbles going along with them. And so we can see that as sort of expected, the injection signatures are very mesoscale. They're just maybe a few RE wide, and they're also only a couple minutes long as they pass through this arc on the night side. But what's interesting is that is when we compare that to the depolarization structure, we can see that a lot of these also start off relatively narrow, but as they evolve, then this depolarization spreads over a wider MLT range, whereas the injections stay pretty confined. And so that's pretty interesting. We'll look into that a little bit more here on this next slide. Okay. All right, so in order to make those depolarization features stand out a little bit more, what I'm doing in this panel is I'm taking, for every point here, the instantaneous BZ value and subtracting off the average BZ for the past 10 minutes. And I'm just sort of denoting that as a delta B sub 10 here for 10 minutes. And so now you can see that depolarization feature really stand out, where you have the two initial BBF onsets here, and we'll look at this in a video in a second, and then that depolarization spread out across over 6, or actually over 8 MLT there. And so we're going to look at this time period marked with the red lines here in this video to the side, where the color contour is the same value, just on a different color bar. The line contours is BZ. And for the arrows, the direction is just V perpendicular, and then the colors are the enthalpy flux. So we can sort of look at all these quantities at the same time. I'm going to start and stop this a couple times to point out some key features. So here now we see the onset of the first BBF, which corresponds to this one right here. You can see an enhancement in enthalpy flux, which we expect. We can see this little excursion in the BZ contour, which means it's carrying some depolarizing flux with it. And this is, sort of what we would expect from a typical BBF. If we play that a little bit more, we see this pileup going on, which is very reminiscent of the schematic from Gabriel's 2019, which is nice to see, of this continual flux being pumped in, building up the amount of flux here moving nightward or tailward. And then I'll just play this a little bit further until we get to the this other sort of set of BBFs here. You can argue it's one sort of breaking up quite close here. And important thing to point out is that you see both injections through the enthalpy flux, but also depolarizations. But what's interesting is the relative scales of those. The enthalpy flux enhancement stays relatively localized to the initial BBF flow region. There's even some return flows, so since we have our interchange occurring, and so we get some flow backwards, but for the most part, the enthalpy enhancement stays pretty localized to the injection. And as we play this video, you'll see that, as indicated by the red color here, this means we're increasing our magnetic flux in this region. So we're depolarizing this whole region across the tail here. We'll play this out a little bit more. And even later, we can see that there isn't so much enthalpy flux anymore, but we're still pumping in magnetic flux into this region. And this plays out, and now we've inflated the inner magnetosphere here. And just to make this a little more obvious, I'll jump back to the very beginning. We can look at these two contours here, where we have one at about 5 and 6 RE. And then by the end of this event, these have now inflated to 6.5 and 8, just to make that stand out a lot. And so this sort of demonstrates the different ways that the injections and depolarizations that are both associated with BBFs evolve very differently once you get to the breaking region and drifts take over. And this can also explain how, might explain some of Runov's observations where you can see a depolarization, but no injection associated with it. This isn't necessarily a different process. You're just maybe observing just the depolarization effects from a BBF that's too far away for you to see the enthalpy flux component to it. Okay, so next we will jump to quantifying the contribution of the BBFs to the ring current. Here we have our familiar enthalpy flux plot. And then what I'm doing is I'm taking the line integral along that arc and showing that as a time series here. This is the net energy flux for any point in time. And then above that, I'm showing the total kinetic energy contained within 6RE, where the blue line is that value and the orange is the time derivative. So we can see how a lot of these features line up quite well. You have your mesoscale injections. This is contributing a lot to the net energy flux. Even though you have lots of return flows, this is still very much a net positive influence on the thermal energy. And then this also shows with the coincidence of this peak and the time derivative of the total kinetic energy that these are very significant contributions to the total energy content within the inner magnetosphere. And so we can see this occurring at several points throughout the time period we're looking at here. And just to try and quantify that, what I want to do is I want to select all the regions where we do have BBFs and compare that to all the regions that we don't, compare the enthalpy flux we get from those. So I'm choosing my BBF regions by looking for I'm flagging any grid points where we have a sudden depolarization, where you have a difference in 10 nanotesla between the instantaneous BZ value and the previous 2-minute average, as well as inward flow. And then any points that are flagged that way, I'm including about half an RE to either side of that, so that we don't cheat and include the return flows that are also a result of these BBFs. Then I'm also including the full minute before that as well, because we're triggering off of the depolarization, even though these BBFs can force down the background plasma that was in front of the BBF further down, which is also contributing. So we want to make sure that we can capture the effect of that as well. And then when I do that, I sum up all the enthalpy flux within these regions versus the total enthalpy flux that we get throughout this time period. This comes out to about 50%. So this is in pretty good agreement with what's been found by Young et al. With the standalone RCM study and from Kramer et al. With their coupled model. And of course, so this is just adding to the current sort of set of data from models saying that these are very important effects, and it would be great to be able to quantify this observationally in the future as well. Okay, so I don't know how much time I have. I'll go over this pretty quickly. Now,
you have time, Anthony.
Okay, cool. All right, so now we're going to look at the effect of these injections on the evolution of the energy composition during the storm. And so here we're going to look at a much wider time range from before the storm onset, around hour 5, through many hours after the end of the main ring current buildup here. So what I'm doing is I'm taking 3 points along the sort of dusk midnight sector, and I'm looking at the cumulative pressure as a function of energy in keV on the y-axis here, and as a function of time at values 3.8, 4.8, 5.8. And I chose these because 3.8 at around 9:15 is about where we get our peak ring current pressure. We want to take a look at that. So just looking at this top plot, we see that we have relatively little ring current to start with. Again, this is dependent on whatever our initial conditions are. Then we have storm onset in this 8 to 10 hour period. It reaches 3.8 around hour 9. And we see this very strong drop in the average energy. I forgot to explain these. The color contour is the cumulative pressure. as a function of energy, and the lines are the quartiles of that. So we can see at the time of peak ring current, we're getting 50% of our total plasma pressure from protons 20 keV and below. Then we see as the storm goes on, this evolves, increases to about 50, and then even to 70 keV as the storm goes on. And there have been some studies looking at how this can be due to the temperature contained within the injections vary over the course of the storm. And so we want to look at if that's what's happening here or if it's some other effects as well, or instead. And so I'm just going into a bit of a detailed analysis on that 3.8 point there. This is the cumulative pressure from the last slide. Up top, we're looking at the line integrated energy flux through that 6RE arc again. We can see that this is where we're getting, the majority of our injections from, as expected. And then it's relatively quiet after that. We get a little bit of another signature here of injections, but for the most part, there isn't. And again, this is just in this specific simulation, but there isn't too much of a whole lot of injections reaching this deep in the first place for any temperature they might contain to really impact this the net population here. And then here what I'm looking at is essentially the flux tube volume, which I'm expressing it in terms so that it would scale linearly with the resulting adiabatic heating you would get. So the idea here is that if we have a lot of compression, that could energize 20 kV population up to 50, 60 kV or so. But we see here there's only maybe like a 20% difference in this quantity throughout this time. And so this isn't enough to explain that jump. But then we can jump down here to the partial pressures, and just so we sort of deconvolve the cumulative aspect of this plot, and then pull out two sort of representative energies, specifically the 10 kV and 50 kV energies. And we can see that we're introducing both on the storm onset, and then the 10 kVs drop over time, whereas our 50 kV protons stay relatively constant. We get a little more of an injection around here. But ultimately, so it seems like in this case, it's likely due this shift in the characteristic energies more so coming from lost processes like charge exchange and the lower energies being on open drift orbits compared to the higher energies. And so this is also just, again, another statement of how important it is for us to get this energy composition right so that we can then self-consistently apply these energy-dependent processes and get a correct behavior of the evolution of the ring current throughout the rest of the storm as well. Okay, so that's all I have. In conclusion, we took a look at how the injections and depolarizations driven by BBFs evolve and sort of disperse across MLT very differently from one another. And that we also saw an example of flux pileup from several BBFs that lead to a more global depolarization. This is very comparable with the model proposed by Gabriel 2019, and can also explain why there's some observations that see strong depolarizations that aren't accompanied by injections, even though these can still both be driven by the same BBF structures, just due to how they evolve differently from each other. This also adds further support that BBFs are responsible for contributing a significant amount of plasma pressure to the storm time ring current, and it will be really great if/when we get some observational confirmation of this. Currently, it looks like the model is accurately reproducing the intermagnetosphere characteristics really well, which is really encouraging. So we can rely on it more for some of our loss process and precipitation. So that's all I have. Thank you very much.
Thank you, Anthony. Excellent talk. Let us open it for questions and discussion. If you could raise your hand, virtual hand that is. While folks are gathering their thoughts, let me maybe start us off with a quick question for Matina.
Jerry, okay, never mind.
Your Paragon, the Paragon concept that you presented overall actually reminded me very early concepts that preceded Van Allen probes, the concept of early radiation belt storm probes that were combining comprehensive in situ measurements of the inner magnetosphere with the imaging components. We all know the history that it didn't materialize due to the constraints and funding. But as you've said, the overall, progress of science doesn't stall, and it's been a couple of decades. So what did change in terms of the capabilities of the ENA imaging that makes this concept more compelling or maybe more timely now than it used to be 20 years ago?
Yeah, so as I said, we are trying now to all the studies that have been with DNA imaging, even the most recent missions are using instruments from 20 years ago. So there have been developments. There are ENA cameras that are being built. I know different efforts. I know for sure at APL we have one. Where you have higher angular resolution, so your pixel size is smaller. You have 2D imaging at a refined angular resolution, and at the same time, what was missing, I think, for many years is high sensitivity cameras, which is very difficult to do with ENA imaging, because the more you open the aperture, so to speak, the more you introduce background as well, if people are interested in instrumentation. So this is one challenge that I think people starting addressing with different kind of technologies. So that's the advance I can see, at least on the ENA part, higher sensitivity, so you can track the dynamic processes, at 30-second resolution as opposed to 10 minutes, for example. And finer angular resolution, so you can track 1 RE images as opposed to 15 RE enhancements of the ring currents.
Thank you, Matina. We have first Jerry and then Howard.
This is for Anthony, kind of in the talk. One of the things that you pointed out in the talk is as you get these versibulk flows going into the inner magnetosphere, you also get these what look like return flows going out. And the question I have for you is, what would that look like, or what needs to happen on a spacecraft to actually be able to detect that outflow?
I mean, I guess.
So if we look back at the RB-SPICE, say, data, what would we be looking for specifically to detect that outflow?
Yeah, well, certainly an outward radial velocity, it would pick it up. As far as the rest of the plasma features, it's kind of hard to say, because you can imagine you're sitting at one L shell, and all of a sudden you have a surge from a lower one. So I guess you sort of need to have maybe some expectation of what the plasma looks like at lower L shells there. I have to think about that a little bit. I guess it depends on how deep you are too, whether you would expect maybe, well, again, it could look like an injection, right? But just coming in the opposite direction, where you just have a sudden increase in your pressure depending on what was below the spacecraft previously. So
would it have a, when you think about the pitch angle dependencies on this, would it have a different kind of look in the pitch angles?
It definitely could, I guess, because your pitch angle distribution within your BBFs are going to be very different from those of the sort of more ambient background plasma. So it would definitely show up in that.
Would it have a different looking pitch angle distribution compared to a BBF?
I would say so. To be
Okay.
fair, I have not thought too much about pitch angle, since I'm limited to, or I focus mostly on RCM land, which is all pitch angle averaged. But
Right.
I would think so, yeah.
When we look at, if we could do a study against some of the RB-SPICE data, or some of the, combined RB-SPICE and HOPE data, It would be interesting to think about what that would look like either in a pitch angle space or a combined pitch and phase angle space.
Mhm. Yeah, I think so. Yeah, definitely.
Maybe it's worth a conversation sometime in the future.
Yeah, absolutely.
Howard, please.
Okay. Well, first of all, those were two great talks. I mean, I was just blown away from some of what I heard. So they were great. I have two comments. For Matina, I was just attending European Space Weather Week this week, and one of the new mission concepts they have is for a auroral, continuous auroral imaging from multi-satellites through the auroral acceleration region, but taking images of the aurora as well. So I just think that sometimes it's really good to have your mission concept where you have everything all together, but sometimes you can accomplish the science by combining different things. So I don't know if you know about their plans, but I just wanted to mention that.
So,
Go ahead.
oh, okay, yeah. So I didn't know that, but as I think I tried to imply during my talk, you're right, you can have a big mission that combines everything, but I also want to advocate for maybe coordination of missions. This mission can go out there, or then another mission comes in, but we are at the state right now where we cannot even refer to other missions when we propose our mission. We have to close everything,
Right.
Closure needs to be achieved with one mission for all the questions we have. So maybe a different approach will help us get there.
Yeah, good. And then thank you. And then for Anthony, I was thinking about the slide, the figure you showed, which showed both the dipolarization and the injections. And it looked to me, I may have missed it, but at the top figure you had, I think that injection and dipolarization, that was about a 10-minute long interval. Is that correct?
Yeah, I would say so. I think most of them are on the order of 5 or so for the most part. Yeah.
Okay, so
They're
that's really
relatively brief.
interesting. Yeah, that's really interesting. And I'm thinking back to questions that always have come up, and maybe they've been answered, and I'm just not familiar with the recent literature. But understanding what controls the size of a substorm and the intensity of that substorm, the location of the substorm, how big it is in general. Those answers look like they can really come out of the modeling that's being achieved now with the level of capabilities of Gamera and the models that you're working with.
Mm-hmm. Yeah, I think so. A really nice thing is that it seems like as we increase resolution, our BBFs stay about the same size, which means we've reached the appropriate resolution to resolve those correctly. So yeah, I think we can start doing these kind of studies in the future.
Great. Thank you.
Excellent. Thank you. More comments or questions? I don't see any new hands. Then I quickly will add to Jerry's question regarding the properties of rebound or bounce flows. Slava put in the chat, first of all, that Themis, since Themis has bulk flow velocity measurements observed these bounce flows. You can look at some literature there, Jerry, and also we recently published a paper on test particle analysis of transport and acceleration of particles inside the mesoscale flows, and we looked at some properties of pitch angle distributions. It could be interesting for you to take a look there. Any last-minute comments or questions? If not, I would like to thank both speakers for absolutely outstanding talks. Thank you. And thank you all for dialing in. And we will do it again in 4 weeks. Please stay tuned to our announcements and have a great weekend. Bye.
Thank you very much.